Hello, welcome again. We are solving some questions of machine design. The topic is brake. Question number 7 and 8 carries a common statement. The statement is a band brake shown in figure is applied to a shaft carrying a flywheel of 300 kg mass with a radius of gyration as 400 mm and running at 340 rpm clockwise. Question number 7. Find the torque applied due to pull of 100 Newton if mu is 0.25. Question number 8. Find the number of revolution of flywheel before it comes to rest. So this is the figure given. This is 100 mm. This is 340 mm. This dimension is 40 mm. This radius is 100 mm. This angle is 75 degree and this angle is 90 degree. Okay. So now drawing the schematic figure to solve it. So that is 40, that is 100 and this is 340. So as this is your 75 and is 90, so 90 plus 75 is 165, and if we subtract it from 360, then it will be, then this angle will be at 195 degree. Okay, so this angle is 195 degree, and rotation of the drum is given as clockwise. This is rotating in clockwise direction. Okay, now when the brakes are applied, then this rope will come in contact with this drum. Okay, as it is rotating in clockwise direction, and so the purpose of the brake is to stop the rotation of the drum. So it will create a tight side here, because um, when the brakes and when the brake and drum, or when the rope and drum are in contact with each other, so this rotation is prevented by applying more tension on this side. Okay, and so the tension, this will be a tight side opposite to rotation of that. Okay. If it is rotating in this direction, then this will be a this will T1 and T2 will cause, because T1 is right side, T2 and T2 should cause anti-clockwise rotation, so that this rotation can be nullified. Okay, so T1 will be your tight side and T2 will be your flex side, and this T1 and T2 are acting on this drum. So they are trying to pull the drum in this direction. Okay, but it is in that distance. So and so this is this T1 and T2 are acting on the drum, and the forces due to this tension acting on this lever is your T1 in this direction and T2 in this direction. So while calculating moment, we will take this T1, this T1, okay, and this T2. Okay, will not take this T2 and this T1, because these are acting on drum. We have to consider the forces on the lever. So that is this T1 and this T2. So now this is your 100 Newton that is applied in downward direction to apply brake. So taking moment about this hinge point, so, uh, that is 100 into 340, that is clockwise. 100 into 340, that is clockwise. T1 into 40, T1 into 40, that is clockwise. Okay, T2 into 100, that is anti-clockwise, and it should be equal to 0. Okay, so that is the moment equation. Now from this T1 and T2, and from this angle, we have T1 by T2 is equal to E mu theta, and coefficient of friction is given as 0.25. The coefficient of friction is given as 0.25. Okay, so it is 0.25, and theta will take in radian, that is 195 degrees. So that is in the radian it will be 195 by 180 into 5. So T1 by T2 is 2.3416, or T1 is equal to 2.3416 T2. So that is the tension ratio. Okay, now we can put this T1 in terms of T2. Okay, here, and find out T2. So T2 comes out as 5367. Okay, and from this ratio, we can find out T1, that is 12567.9. All are in meters. Now to calculate braking torque is nothing but difference of tension multiplied by radius, P1 minus P2 to R. So that is 12567 minus 5367 into radius is 110. So that is in Newton mm, or in Newton meter it will be 792.1 Newton meter. Okay. So that is your braking torque. Now we have to calculate the moment of inertia of the flywheel in second part. So we know that the moment of torque is equal to I into alpha, and I is your moment of inertia. Mass of the flywheel is given as 300. Mass of the flywheel is given as 300 and radius of the region is as 400. So moment of inertia will be 300 into 0.4, converting into meter, 0.4 here, that is 48 kilogram per meter. From this I and from this torque, we can calculate the angular acceleration of the flywheel when the braking torque is applied. Okay, so angular acceleration comes out as 16.5 radian per second. So now this is the angular acceleration of drum, or angular retardation of drum, because uh, drum is coming to rest when the brake is being applied. Okay. So we can apply that formula, that omega f square minus omega I square minus is equal to 2 alpha theta, where omega f is your final speed, omega is your initial speed, and alpha is your angular acceleration, and theta is your angle turned during braking. Okay. So now omega I is given as in RPM it is given as 340. So in radian per second it is here 35.6 radian per second. Okay. Now if we put the value of omega I here and take this negative, alpha is negative because it is retardation, we can find out theta. So theta is your 38.41 radian. Okay. So 38.41 radian. So this is the angle turned by that drum during braking. So in one revolution in radian. Okay. So in one revolution the radian is 2 pi. So number of revolution is 38.41 divided by 2 pi, that is 6.1 revolution. So after applying brake, the drum will stop after 6.1 revolution. So just we have to find out braking torque, then equate it equal to I alpha. We can calculate because mass and radius of variation given. Then it is alpha. Alpha is your negative or retardation because drum is coming to rest. So now final velocity will be 0. Initial velocity is given. It is rotating at 340 rpm. Converted into radian per second. Find out theta and then find out number of revolution. Theta is the angle turned during braking, or if you want to find out number of revolution, in one revolution angle turned is 2 pi. So that is your 6.1 revolution. So answer is 6.1